Hey guys, it's Coach Zane here, and in this video I'm going to be explaining how to make your robot drive perfectly straight using the Spike Climb app. So you would have noticed that if you simply use the basic pink blocks to drive forwards and backwards, your robot will have a veer side to side. Now this can happen for a multitude of reasons, but the main thing is how do you make sure that the robot goes perfectly straight all the time? And the answer is pretty simple. You use the internal gyro in the Spike Climb hub to make the robot drive straight. So in this video I'm going to be showing you how to program that into your robot and how to make your robot go perfectly straight so you can achieve more missions, more points if you're doing this for FLL or just in general for fun if you're just doing some learning. So this video is going to be broken up into 3 parts. After this introduction, I'm going to be doing a short explanation on what the gyro straight actually does physically. I'm going to go over to my iPad and explain that. After that, I'm going to then go into the code and show you how to code this gyro straight perfectly for your robot so that it's going to move straight. I definitely recommend watching the explanation because not only is it important to learn how to code it, what's more important is learning how it works and understanding the process, because understanding that is going to let you use those skills in future aspects or whatever you need to do. But without further ado, let's move over to the iPad and let me explain what the gyro straight actually does. Okay, so we're here on the iPad and now we're going to very briefly just explain the understanding of what's going on with this gyro straight. So to understand, the gyro straight is a solution to a problem, but what actually is the problem? The problem is when the robot is moving, as you can see, I've got like a little sketch here of the robot. When the robot's moving, we want it to stay on this 0 angle, as you can see over here. So when it drives just with the basic, purple blocks, it'll drive like this. And slowly, it'll, start to veer off track, right? And it'll go, quite different to its destination. So if its destination is somewhere over here, it may actually end up somewhere, to the left or to the right. Now, this is quite exaggerated, but the fact is, over different straights with different turns, this can, this inaccuracy can really add up. So what this is a change in angle, right? So instead of landing on the 0 angle, it deviates by about 2, maybe 3 degrees. And this is calculatable. Like, you can take this number and you can calculate it, and we'll get to that later. But let's think about why this happens. So why is there a actual deviation, or what we call this is veering? Well, it veers for a certain number of reasons. There are actually a few. The weight imbalance, so that's the first thing. If you have more weight on one side of the wheel than on the other side, then it will veer toward the weighted side because that wheel applies more force to the ground. Traction slippage, this is similar to weight. So sometimes what can happen is this wheel will actually slip from the ground because it doesn't maintain its traction, its friction with the surface. And the last one is power discrepancy. This isn't as much of an issue with Spike as it was with EV3, but sometimes it can output, the hub can output different powers to the wheel. So one wheel may actually be turning at 94, 93, whereas the other one's turning at 100. And so that power discrepancy becomes a bit of a factor. So these are 3, main factors. And that's the real problem, right? We now need to fix this. So how do we solve this? I said that, we can calculate the angle of the deviation, and to do this is with something called yaw. So yaw, you can think about yaw as angle. When I say yaw, I just mean the angle of the robot. So right now, like we had the example last time, if this is 0 degrees, then the yaw angle here is simply 0 degrees. Okay, over here, right? I'll do this example next. Over here, the robot's actually turned, so before it was like this with the wheels like that, the robot's actually turned about 90 degrees, right? So the yaw angle here would simply be 90 degrees. Now we have somewhere here, this is somewhere in the middle, this case over here. So, I haven't calculated this with with a protractor or anything, but we can roughly say the yaw angle here is 45 degrees. It's somewhere in between 0 and 90, right? And it seems like straight through, the middle, I guess. If you were to put lines here, if that's 90, it seems about halfway through 90, which is about 45 degrees. So that's where that comes from. And that is the yaw angle. So with the yaw angle, all you need to know, the angle of the robot is simply the yaw angle, and we can actually calculate this. So there's an internal gyro sensor in here, and what this does is it'll take the input of the position, it'll set it at 0, and then if it deviates, which you can see here, it's actually able to calculate, I've deviated 2 degrees. So what we're going to do is we're going to use the internal gyro sensor, and we're going to use some mathematics and some programming to actually fix it, and that's where the gyro straight comes from. So a little note over here, pitch and roll can also be calculated. So yaw is basically the angle side to side like this. pitch and roll are just the angle like this and like this, right? This is why you may have seen the specifications. This has a 6-axis accelerometer, which just means it can calculate not only with these two axes, there's this axis over here, these two, and these two over here, but it's highly unlikely your robot in an F-law competition, it's gonna go like this, right? Which is why it's only, you know, very important for you to calculate the yaw angle. So we can pretty much disregard pitch and roll, but they can also be calculated, and it's important for, you know, other fun tasks like balancing and whatnot. But anyways, now we get to the crux. So essentially, we're gonna follow a rule. This rule is gonna be the correction is going to be 0 minus the yaw angle. Now this may be a little bit confusing, so let's do an example. We said this is the robot, okay? And the robot, it'll start. So this is without the gyro straight. The robot will start and it'll veer off track. So we have a little slight veerage over here, this, you know, deviation. Let's call this 2 degrees. Let me make that a little bit more neat. So this 2 degrees is calculated by the yaw angle. So the yaw angle right now is actually 2 degrees. So what we're gonna do is we're gonna do some math. We're going to go 0 minus 2 degrees, and that follows this rule over here. As you can see, this is the correction. What's 0 minus 2 degrees? -2. Okay, so then what it will do, will then steer back, right? Like that. And because, you know, the reason why it does this is because you've gone off 2 degrees, the robot now wants to go 2 degrees back on track. That's the basic idea of the gyro straight. It'll take the error and it will do the opposite, like it'll minus the current position with the yaw angle, and it'll minus that and it'll do the opposite. So it's gone back off track, now it's -2 degrees, and now we're back on track, right? So let's say it's going now, it's going fine, and then we'll veer this way. If this was 2 degrees, let's say this is maybe -1 degree. Okay, the rule also still applies, right? So the rule is the correction equals 0 minus the yaw angle, which is 0 minus, and then we have -1, and that equals 0 minus -1. These two negatives make a positive, which is 0 plus 1, which equals 1 degree. So it veered off -1 degrees, it's then going to go back by 1 degree over here. This is the basic idea of the gyro straight. This is what we call proportional logic. Now, that's just the name of this. You know, essentially this is essentially a proportional logic, right? The rule that it follows is called proportional logic, and proportional logic is used in a lot of different situations in real life. It's also used not only in gyro straight, but also in the line follower, which there'll be a video about that as well. So it's very important to understand what proportional logic is. In essence, whatever mistake the robot makes, we're going to do the exact opposite to get back on track. That's all it is, really. Fundamentally, it's just proportional logic. Now, there is a, you know, small, update that we haven't really explained. Basically, what we do is we take the correction value. So this correction over here, we take the correction and we multiply it with something called the GSPK. So I'll briefly explain this because it's quite important and it comes up in the program. The GSPK is called the gyro straight proportional constant, but simply it's just a number, right? What this number does is it controls the rate of corrections. So let's just say the correction for whatever number it is, let's just say we're going to do correction multiplied by 1.5. So this is going to be situation 1. And then situation 2, we're going to do correction multiplied by 0.5. So the GSPK is just a number, and I've chosen 1.5 in situation 1 and 0.5 in situation 2. What is this? Well, let me now explain the difference between this GSPK, the high and the low. So as you can see, we have a bit of like a curvy fashion with the gyro straight because it maintains its straightness, right, by going back. With a higher GSPK, what it will do is it will actually do more of like sharper corrections like this, right? As you can see, the corrections are very sharp and there's a lot of different like wiggles, right? With the robot, it goes like this. And that's what a higher GSPK does. It increases the rate of corrections. What does a lower GSPK do? So I'm going to choose a different color. Let's go with green. A lower GSPK will kind of make it a lot more curvy like that. So the purple is actually situation 1. So I'll highlight that like that. And the green is situation 2. So with a lower number here, it has more of like a slow rate of correction. And with a higher number here, it has a much faster rate of correction. Now, if that doesn't really make sense, it doesn't matter. All you need to know, higher GSPK, faster corrections, lower GSPK, slower corrections. That's pretty much it for the understanding. So if you have understood that, then you're pretty much ready to program. If you haven't, maybe rewatch it, ask questions down in the comments below and I'll try to get back to them. So without further ado, let's go over to the laptop and actually program this out. Okay, so now that we are back from the iPad onto the laptop, let's actually code the gyro straight and make sure that it's going to work for your robot. So coding it, we're going to be using word blocks in this video. So we'll create a new project, and you would understand if you watched the previous video, you may already know the interface. If you don't really know what's going on here, I definitely recommend watching the basic movement video because I explain, from top to bottom exactly what this setup is, and we'll be using a few blocks here, which I also explain. So without further ado, let's go into the code. So when you're coding a gyro straight, naturally you always need to do the basic setup, which is setting your motors. So I've got my motors set up to A and E for this video, and we'll swap them around. So make sure your right is in the right section, E, and your left is in the other section. If you're having some troubles, just click it, play around with it. You'll see that it gets a little bit annoying, but with enough tries, that's E and A. So let's go click it again, A and E. All right. So now that that's done, we're going to hold position at stop, which is something that I explained in the previous video. So we'll go and we'll hold position. This is just going to allow us, the robot, to stop when we want it to, precisely, because it will have some gradual power if you put it to coast, or it'll break and actually do a bit of like a jerk if you put it to brake. So we're going to put hold position, and after that, now let's move to the actual the gyro straight. So essentially all we need to do is put a repeat block. So this repeat block, what this loop is essentially it's going to loop over and over again the same command until we want it to stop. So we're going to go to the More Motors tab, and we're going to pull out the Start Moving block at 50% speed. You'll notice that we have the straight command, which we want, and we have the power command. The third thing we need to do to go straight is the distance, and that's not included in this block. The reason being is we're going to control the distance up here, and when this distance has become satisfied, that's when the loop is going to stop. So we're going to move straight at 50% power. Now, how is the gyro going to be, in this? It's quite simple. We're going to go to our operators, and I explained this in the explanation before, but we're going to essentially do a operation with a minus. So let me pull that out. Okay, and what's going to be in this? We're going to put 0 here. And as explained, we're going to be using the yaw angle. So to find the yaw, we're going to go and get here, and we're going to change this to yaw. Now, yaw is simply the angle of the robot, as we explained in the explanation, and we're going to push this into this straight block here. So as you can see, it's already looking a little bit hectic, a little bit fancy. I'm going to explain briefly what this is doing. So it's going to start moving at 0 minus the yaw angle. So as explained, if it goes straight and it veers off, the yaw angle is going to be about 2. 0 minus 2 is -2, and that's plugged into, if I pull this out, the steering, right? So it's going to steer back -2. However, we have this command in here to do it for us. So it's going to kind of go straight again. And it's going to go at 50% power. Now with the gyro straight, you kind of want to go a little bit, conservative with this, maybe 40%, even 30%, if you really want to be accurate about things. Now, as I explained before, this isn't perfect yet because we haven't actually completed the program. It'll just run, but it doesn't know when to stop. And we're going to stop it whenever we want our distance to stop. So with distance, we're actually going to be using something called relative position. Relative position, it essentially allows us to go 0 to 1,000. Whereas if you just use regular position, it won't actually let you run to, it'll go 0 to 360 and the loop will go over again. So with setting up relative position, the first thing we need to do is set our relative position to 0. And we're going to set this to our any one of the wheels. So our wheels are in A or E, just choose one of them. It doesn't really matter which one. We're just going to choose A. And now that the relative position is set up, the next thing you want to set up is your yaw angle going to 0. So let's go back up here, set yaw angle to 0. This is the setup for our gyro and our wheels. Now let's actually code in the distance. So for the distance, we're going to be using a greater than block. Let's go here. And we're going to get greater than 600. What is the 600? Well, we'll go to more movement here. And the 600 is going to be the relative position of A. So let's go pull out this block, put this in here. So If A has moved up to 600 degrees, that's when this loop is going to stop. This block is going to move until A has reached 600, and then what is it going to do? Pull out a stop moving block. It's going to stop moving. So this gyro straight now, it's going to travel at 40% power at 600 degrees, right? If you want to go higher power, increase that. If you want to go for longer, just change this to 1000, right? Or less or more, whatever you want to do. This is now going to go perfectly straight, right? It's going to have a little bit of a curve, but generally speaking, if you've got, it takes some fine tuning as well, but generally speaking, you know, this will kind of go the way you want it to. Now, this is the basic version of the gyro straight. All it does is it'll go straight. It won't really adjust things according to your robot. And now we're gonna, you know, update this or upgrade this program to work a little bit better. Okay, so what are some problems with this program? First things first, this is going to repeat until motor A has reached greater than 1000 degrees. So it may actually go like 1003 and then stop. That, you know, extra 3 degrees, you may seem like that's nothing. It'll be more like 1010. 10 degrees is a big deal in terms of inaccuracies, and it actually builds up over time. We want it to stop when it's actually greater than or equal to 1000 degrees. And things are going to get a little bit hectic, a little bit crazy here, but don't stress. We're going to put an OR, right? After this OR, we're going to make this, go to more movements, and we're going to pull out a relative position again, and then another operator equal to. And you can maybe see what's happening here. So we're going to go A equal to, and we're going to put 1000. These numbers have to be the same. We're going to pull that out. So it's going to be greater than or equal to 1000 degrees. And we'll pop that in here. So as you can see, it's going to repeat until it's either hit 1000 degrees or being greater than 1000 degrees. Now you might say, what's the point of this one greater than, right? Like, it's not necessary. As soon as it hits 1000, we want it to stop, and that'll work. Well, not really. These wheels move really, really fast. And actually, it'll go up to like 900, 980, 990, 999, and then it actually may skip over 1000 perfectly. Like, the hub may not actually recognize it's hit 1000 degrees because the wheel's going so fast. So this greater than is like a backup measure. If it doesn't actually read an equal to 1000, we're going to put a greater than as our safety precaution, so that as soon as it goes over 1000 or equal to, we're stopping the program and we're good to go to the next, you know, set of movements or whatever it is. So that's the first change we need to make. It looks a bit crazy, but it's actually pretty simple. It's just stopping at 1000 degrees or a little bit greater than 1000. Our next one is a little bit more advanced, but it's still really important to do. So we're going to go here and we're going to pull out a multiplication. I'm just going to create, you know, this change, and then I'll explain it afterwards because it's a little bit complicated. But nothing that you can't learn, I guess. It's pretty simple once you break it down. So we're going to take this, you know, the minus out, and we're going to put it in this multiplication block. So I got this out of this third one here. It's a little star. It's quite small. They should actually make that bigger. But anyways, we're going to multiply this, and we're going to multiply it by 1.5. Okay, and now we're going to put this whole thing back and replace it to where it was. Oops, that came out. Let's go and pull it there. Done. That's the second change. That's it. What does this change do? What we've done is we've taken the correction, right? So remember that 0 minus the error, it will be like minus 2. We're going to multiply that by some number, right? For the sake of math, I'm going to change this number to 2. What this will do, the higher this number is, it's going to move faster back into the correct spot. So let's say it's going, it'll quickly move, you know, it's going this way, it'll move straight, it'll make a faster correction to the straight line. Whereas if this number is, let's say, low, like 0.5, it's going to make a slower rate of correction. So it's going to like curve to the straight line. Now, you don't want to make this crazy. Like, you can't just make it like 100, because what that'll do is it'll just start zigzagging, because it'll think it's making like very big corrections, and you can't make it too low. You can't make it like 0.1. Then it will just do like really slow corrections, and it won't even actually get back to its line, its straight line. So what you want to do is you want to change your robot, change this number. It's going to be different for everyone. We call this thing the gyro straight proportional constant. It's called a constant because it's just a number, and it's proportional because it changes the rate of correction. So with every robot, it's going to be different. With this robot, I found that 1.4 or 1.3 works pretty well. I'm just going to go with 1.4. You may need to do some tests, right? Try it at 1.5, try it at 1, try it at 1.25. Go up and down and, you know, do different tests to see what works best for your robot. I've seen it at 1.4, it works pretty good. And that's it. That's the whole program. So without further ado, let's see what this program actually does. as you can see, it was quite simply a straight going forward. So it goes forward, and then that's it, it's done, right? It's not 100% perfect, but I was hitting it pretty hard, and you can see it actually came back to the position perfectly. If my hand wasn't there, it does a pretty good job of maintaining its position with, you know, the natural errors that we explained before, like, you know, the wheel slippage and the weight imbalances and that kind of. And that's pretty much it. So thank you guys for watching this video. If you found it helpful, definitely continue watching. You know, there's more than just the gyro straight. You can also learn line following, you can learn gyro turns, you can learn line squaring. This is just, you know, the first, or, you know, if you watch this out of order, the second or third in many skills that you can learn to make your robot become more accurate on the FLL map. So I guess I'll see you guys in the next one.